that can be defined Is that 1 over pi okay, or it was pi in the top? Top?
No,
it's okay. And this is exactly equal to minus I sine C Fourier transform. Okay. Then we discussed several things about the Hilbert transform that is continuous from LP to LP. We proved that. But one thing that we will use a lot is the following result. Is theorem due to Calderon and say the following. If you commute the Hilbert transform with a multiplication if P is between 1 and infinity, and you commute the Hilbert transform with a multiplication by A, then you have that this is an operator of order 0 in F. This is an order 0 because this is homogeneous for order 0. Multiplication by A is of order 0. This is of order 1. When you compose these two, you have of order 0. That means that this is of order minus 1. The second thing that we study, and it was a maximal, Hardy-Littlewood maximal function. And that's defined in this way. The maximal function, if f is locally integrable, the maximal function of f at x is the supremum over all balls that if you want it, this is the supremum of the character 1 over the characteristic of this ball convolution with absolute value of f. And this is the operator that controlled most of the business. In fact, a few remarks. If you have phi is positive, radial, non-increasing, and you take phi of t of x equal to 1 over t to the n, typical kernel, then you have that the supremum for all t of this convolution with f, it will be bounded by this quantity. Then you have any nice kernel that is positive, radial, and not increasing, and you take the dilation, preserving the L1 NOR, the supremum of this. Also, we saw that if you take the maximal function that is not centered, these two are equivalent. is instead of taking all the balls that you center, you take any ball that contains this. These are two are equivalent. There is a constant that depends only on the dimension that pass this. Then these two quantities are equivalent. And we prove that you are almost, this operator, and even that is nonlinear, is sublinear, is continuous from LP into LP from any P different than 1. Okay. With this, using that, we sketch the proof of this lemma, or this theorem, that is hard deleted with Sobolet. Let's say the following. Suppose that alpha is between 0 and n. Suppose that 1 over p. 1 over q is 1 over p minus alpha over n. And p and q, and of course, this is 1 half, 1 6, 1 6. There it is. Then, f in LQ is less than some constant depend of alpha, n, and t. D alpha of f. Okay, we prove that using a trick for the maximal function. Okay, we will use that later on. We are going to use all this later on. The last thing that we want to discuss before we start with the real matter will be the following question. And we will not go into all the details because this is a chapter. In fact, there are some books about weighted inequality. But we want to study the following question. Suppose W is positive, W is local integrable, and you ask yourself a question. Conditions to have this inequality, that the maximal function of f in LP with this weight is less than this. You are asking what the condition you need about this density such that the maximal function send LP into LP. Okay, and we will use that later on. Okay, what is the condition that you need for this? For all f in LP with this norm. Okay, let's deduce this necessary condition for the moment. And since these two functions, the maximal function center at the ball, or the maximal function that point contained on the ball are equivalent, let's do that with this maximal function. This is saying this is less than a multiple of this, and this less than that. Okay. Suppose that, let's go this way now. Suppose that we take any ball. This is a ball in Rn. Suppose we consider f multiplied by the characteristic of this ball. Right? Therefore, we have the maximal function of the maximal function is positive, but let's write it like this one. Okay, another constant, let's put C prime here. This is a different C than the other one, and this is the ball. Okay? We apply, suppose this is true for any function here, then we apply to this particular function. Okay, but see, we have that what do we know? That if for any x that belongs to B, this is more than the average. Because the maximal function is the supremum over all possible balls. Right? This is the average of f. The average of f over this ball. Then we have that for any x in this ball, right, we have this is larger than this. This quantity is larger than this constant. So let's write everything. The average over the ball of f multiplied by the average of f over the ball multiplied by the integral over the ball. If you integrate over the ball, this quantity is more than this to the p w of x dx. Is this clear? For any point on the ball, this quantity is larger than the average. Then you can take this one out. You have a lower bound, and you are integrating only this, and I have 1 over p, right? Okay, then I have to put here. Let me start with this. Then if I start like this, I have p here. Is this okay? And this is the measure of the ball according to this. Then you have the average over b of f by the measure of b is less or equal to this quantity. We can put y here. Okay, let me see. I don't want to get lost. Therefore, we have the average. This is the average over the ball of the absolute value. In fact, I mean, this is the average of the absolute value because we put dy to the p is less or equal to 1, this constant Is this clear? This is the average. I pass dividing this here. Okay, now we are going to we have the right to choose F whenever we please. We are going to choose F such that these two quantities, these two integrals are equal. That means that we're going to choose F. Past this here, it will be F of y 1 minus p equal to W. That means F of y is equal to W 1 minus p. Okay? The average. Oh, no. I have to divide right through. Thank you. Then what? And this is okay with the maximal function. Thank you. I mean, this is the average. I mean, this is right. The average. I forgot this part. Thank you. Please correct me. Then I wrote that here. I pass this here. Now I choose these two integrand to be the same. Okay, then if we substitute here, what do we get? Then if we substitute there, we're going to have that 1 over b, the measure of b, integral over b of f. F is all this. P less or equal to this quantity that we have here. But we choose that, and this one is going to be this. Is this okay? Therefore, if we move this to this side and this one to this side, we get this. W of b, I'll say to this, 1 over p, integral over this, W of y, 1 minus p to the p minus 1. And now I'm cheating, right? What am I cheating? Well, I have power p of this. I have power p minus 1 here. I have to put this like this. Okay? This part here. Then I have 1 over b, power p minus 1. I have a p. I have this. Then the condition is that for any ball, this is 1 over the ball. This is the measure of W over the ball. Multiply it by 1 over the ball, the measure of the ball, the integral of W1 minus p dy p minus 1 less or be bounded, the supremum over all balls. And this is the AP condition. This is called the AP condition. And this is due to Markenhaus. Any question? Then to have this, then the conditions say the following. You satisfy this, imply that the supremum over all balls of 1 over the measure of the ball integral over W multiplied. Okay, if you want, you can write it. Is that the way I wrote it? 1 minus P. P minus 1. These have to be bounded by some constant that depends on W, and this is a P. Well, it comes out that the theorem is if and only if. But we are not going to prove that. The only way that you have continuity from LP into LP with this weight is the way satisfy this condition. I mean, it's not terribly complicated to prove the other side, but when we will have to spend a few hours. Okay. And we will use that. In fact, we're going to use a little bit more sophisticated result, but let's not get into that yet. In fact, we have the following theorem. And this is more general, but in our purpose is for Hunt, due to Hunt, Markenhaus, Whedon. You say that the same business is true if instead of put the maximal function in one dimension, you put the Hilbert transform. And there is no more Rn here. Then you see that the maximal function is one control everything. Then if you want the Hilbert transform to be continuous from LP with this density into itself, you need that this density has to satisfy this condition, if and only if. Okay, I think that will finish the requirement. This is a very nice, and the way that not proof is that you start with the maximal function, you deduce this, then you prove that this is sufficient for this, and then you try to control the Hilbert transform with the maximal function. Okay. Now let's go to what we want to prove. Is the Hardy principle, uncertainty principle without using analyticity. Okay, let's recall what is L2 Hardy uncertainty principle. If you have a function that we are in L2, this and his Fourier transform below to L2 in Rn, A and B positive, then if A times B is larger than 1, imply that F is 0. And that is sharp. Okay? And we don't want to prove it this way. We go to the free Schrodinger equation. And we saw that in that regard, the result, you have that the solution at the time t is equal to some constant then what you are saying is, if you think that this is f, then the solution is the Fourier transform of f, of course, evaluated in this point. Because this quantity doesn't change anything, it has absolute value 1, this is a number, you are proving this for a fixed t. Then you can rephrase the uncertainty principle in L2 using this function, and the statement is this one. If U0 belongs, if exponential of a pi x squared of U0 and exponential of b pi fourth pi times a square x squared of u at the time t belongs to L2, a b positive, if a times b times 4 pi t squared is larger than 1, imply that U0 is 0. Okay, you are rephrasing the first two lines into the solution. Okay, and these are equivalent. Okay, you can choose, so you give me an f, I choose the u such that this is equal to f, and so forth. Okay, let's do some simplification that will be removed in some moment. Then it doesn't make any difference what t you choose because you can move the t around. Then, with a lot of generality, assume t equal to 1. Then we want here, we are here, we are here. I mean, when you have the t here, what does that tell you is that this constant has to be, I mean, if you want the solution not to be 0, this constant has to decrease with the t. And the second, since we will show that it suffices to take A equal to B. There is something called a conformal transformation that if you have A and B are different, you can do some transformation and do there. Then let's rephrase that. If A is equal to B, and if you have this constant, you have. You can choose, and there is. Okay, in fact, I have to be careful because I want the two to be exactly the same. We were here, right? Okay, I want this constant to be equal to this constant. That's what I want. Then, how do I have to choose this? Then I want A to be equal to B 4 pi squared. Then the condition is that this is the theorem that we would like to prove if E by B 4 pi, I want to choose A and all this. If exponential of A pi x squared by U0 and exponential of A pi x squared U1 times 1 are in L2 in Rn, and A is positive, and the condition now is this was a square here, right? If A is larger than 1, imply that U0 is 0. I think, let me check my notes to be sure I don't know. Let's see, and is this okay? Is this okay? Okay. 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 Now let's prove a theorem very close to this one, not as sharp with this constant, without using any analyticity. The proof of this, if you missed the class, we did some version of this that was proved by Hormander and Berlin, and he used complex techniques, right? The Franklin-Lindelof theorem and so forth. Okay. Let's try to prove that without using analyticity, and all the proof will be formal. And then we have to justify that, and for that reason, we will use some of the techniques that we discussed previously. Okay, suppose, let's start here. We want to solve this problem. But we want to know what happened when you multiply by a Gaussian here. Therefore, you define u of xt is equal to exponential of some function of xt by f of xt. Phi to be chosen. Or if you wish, you can say that f is equal to exponential of phi multiplied by u. And you want to know that this one is in L2. This will be something like x squared. Okay. Then formally, what is the equation that f satisfies? Then, well, you go here. dt of u is equal to exponential of minus phi multiplied by minus dt of phi plus when the derivative hit here of t, when the derivative hit here. And when you put the Laplacian here, it will be, when the Laplacian hit here, then when one hit here and the other hit here will be -2, gradient of phi, gradient of f. And then when the second derivative hit the exponential, then you have to, let's see, and then when you take the second derivatives of this, you're going to get, if the derivative hit here will be this. If the derivative hit this one will be then you satisfy this equation. Therefore, your f satisfies this. Remember that this function phi depends on x and t. It's okay. Okay. Suppose the key of the matter, and then we will finish. If h of t is the L2 node of f, square, then you have this estimate. Well, I have to choose before, I choose that, and I define, and suppose that if this is with the choice phi of xt equal to mu x plus r t 1 minus t E1 squared. E1 is the vector in the first coordinates. Okay. Suppose that you choose your function to, the function in the exponential will be this one. Who is r, and mu will be positive. And you will see you are choosing that in t equal to 0, this part doesn't count. In t equal to 1, this part doesn't count. After a while, you will see that this is the right choice. Suppose that we choose this. And we define h this way. Then claim the second derivatives of the log of h let me write it this way, is larger than -8 r squared mu. What is exactly to say that the second derivative of a function is positive? Is to say that this function is convex. What you are saying is that the log of this function is convex, but it's not convex, it's not positive, but it's bounded below. Okay? Okay, suppose that we have proved the claim. Let's complete the proof assuming the claim. Assuming the claim, let's complete the proof. then all the matter is to prove this claim. Let us finish the proof. Okay, I don't want to erase that. Okay. Okay, what is, to write this is the equivalent to write this. It's possible. The second derivative of this is positive. Why? Because what is the second derivative of t1 minus t? Is equal to minus 2. Right? If I pass to the other side, r squared, yes, thank you. Okay. Then what is exactly that this is telling you? It's telling you this is equivalent to say that h of t exponential of minus r squared t 1 minus t over 16t, 16 mu, this is logarithmically convex. What do you mean logarithmically convex? Means that if you take the log, it's a convex function. Take the exponential there. Is this okay? This is exactly equivalent that f of t is less or equal to f of 0 multiplied by 1 minus t, f of 1 multiplied by t. This is exactly that to be logarithmically convex. In particular, that tells you that at t equal to 1/2, you get that f in 1/2 is less or equal to f of 0, 1/2, f of 1, 1/2. Okay, let's write what is this. Who is f of 1/2? Okay, f of 1/2 is, this is an integral in x that have, and this is something that x doesn't appear. You're going to evaluate this in t equal to 1/2. This gives you 1/2, this gives you another 1/2, 1/4. Then this is exactly exponential of minus r squared 64 mu integral of exponential. And now let's go to definition of h. That is the L2 norm of f. That is this one with this weight here. Then it's mu x r e1 over 4 square u of x 1/2 squared dx. Okay, this is f of 1/2. To the power, maybe it was 1/2 here. Let's put a square here. Let's take the square of all this. I mean that we go like this. Okay, we take the square. We have to take the square of this. What is the square of this? 32, right? Okay, this is less or equal to f in 0 f in 1. Okay, f in 0, this when you put 0, that doesn't count. F in 0 will be whenever you have this one in 0, this doesn't count, it will be this one. Okay, I think I'm doing something wrong. Because this is already the L2 nor. If I put, let's not take a square here. Let's put it like this. Because this is already the L2 nor square. If I take a square, then there will be 4 here. Then it will be too complicated. Let's do it like this. 64. Okay, this is already the L2 nor square. Then I don't have to. Then I put 1/2 here, 1/2 here. This is 1/2, 1/2. Is this okay? This is the L2 nor square. And now with the 1/2 is the L2 nor really. And this one is the L2 nor really. And this is the L2 nor square. Then we have this. Okay, this is our hypothesis that this is finite. Okay, we will go back and match the mu with the a's and the pi and so forth. Okay, but this is finite. This is okay. Therefore, I can pass this to the other side. Then we have that the integral over exponential of mu x plus r equal over 4 squared u x 1/2 squared dx is less or equal. I pass this to the other side. Exponential of r squared over 64 mu Okay. Are you with me up to here? No? 2 more lines, we finish. Then this is an integral in the whole domain. Then suppose that I integrate only in a smaller domain. I integrate in the ball of center 0 and radius r. Radius 0 radius r over 4. I'm not integrating now in the whole domain. I'm not going to integrate now in the ball of center 0 and radius epsilon r4. Epsilon is going to be very small positive, and r is the same business that appear here. Okay, if that means that we are integrating for x less or equal to epsilon r over 4. Then how is this quantity? If x is less than epsilon r over 4, right? This quantity is absolute value r over 4. Then you have this is r over 4 minus x, and this is larger than r over 4 multiplied 1 minus epsilon. Okay? Therefore, this exponential that you have there is larger than r squared over 16, 1 minus epsilon squared. Then this is larger or equal. Now this part is, you have a lower bound that is independent of the x. That goes out. Therefore, this is dx exponential of r squared 1 minus epsilon squared over 16 multiplied by mu. Are you with me up to here? Therefore, if you pass this to the other side, you're going to have, therefore, the integral over the ball of center of the L2 north of the solution at the time 1/2 is less or equal to exponential r squared over 64 over 16, if you wish, multiply there by 1 over mu, multiply here by mu 1 minus epsilon. Okay. Let's see if I have everything. Okay. 64, and I have here okay, do I have a mistake? 8 mu 1 minus epsilon squared. Is this okay? Multiplied by something that is bounded, that is the data. Okay. What did I have? You say that this is 4? 4 times this is, yeah. Thank you. Okay, let me say 1 second, 1 second, 1 second. Where did I get it to? Okay, 2 mu. Okay, if I want to be very picky, this has to be a 2. Why? Because this is the L2 north of F. F has one of these in each side. When you take 2 exponents, they add it. Okay, I mean, who is F? Is F is this one multiplied by his conjugate. This is real. Then you have this, two factors of this that give you a 2. I mean, it's not a big deal, but it's a 2. There is a 2 here. Okay? There is a 2 here. Let's see, there is a 2 here. Is there is a 2 here? Yes, because you have this at equal to 0. There is a 2 here. Since we want to know how far we are from here, we have to be careful with the constant. Then we have this is the L2 node of this that have a 2. I mean, you write it like this, you have the 2, you don't have the 2 here. This is okay, we have a 2 here. Then we have a 2 here. Therefore, this is, now I get 8. Okay? I mean, we are not going to get anything sharp, but and we can put this like this. Okay, suppose that I can choose epsilon, so suppose that a mu squared is less than 1. If then there exists epsilon such that this is true. I'm sorry. I want this to be negative. If this quantity is more than this, then this is... Okay. What is exactly that I want? Okay. We finished, by the way. We are here. I want to say if this quantity is more than 1, still multiplied by this number, this will be all negative. You want to 1 minus a mu squared is less than 0, then for epsilon sufficiently close to 0, this quantity will be negative. If this quantity is negative, take R2 goes to infinity. Right? This doesn't appear here, the R doesn't appear here, the R. When R goes to infinity, what do you get? Let R goes to infinity. This part is going to go to 0. This is going to go to the whole domain. Then you have that this function have L2 node 0. Therefore, it's 0. Well, if you are 0 in some moment, you have to be 0 after that. Once that you have fixed that epsilon, you take the R goes to infinity, and you get the result. Okay, let's see what is exactly that you have proved here. We are still missing the claim, but let's try to compare with this constant. We have proved this. We have proved this. If a mu of x squared by u0 and a mu by x squared u1 are in L2 in R, and mu is positive, of course, and a mu squared is larger than 1, then you are 0. Okay, let's rephrase this with the pi and all these things. Then recall, instead of call it mu pi to have it the same. Our new mu is mu pi. Then 8 times quarantine is you multiply by pi and divide by pi. Then what you have is, let's see if you agree with this condition. I multiply by pi and divide by pi. My new mu will be mu over pi will be this. Okay, I have this theorem. Then I have this theorem. I multiply by pi and divide by pi. I multiply by pi and divide by pi. And I want a condition of this constant. Right? Multiply by pi squared. Then I multiply by pi squared in both sides. And this is my new constant, right? Therefore, I have okay. Is this what we have or not? Then it's supposed to be nicer than this one. I mean, the number is not as nice as this one. Let's see. Okay, let's be sure that we are doing. We don't get. Okay. This is what we have, and I want to put the pi to compare with this. Therefore, the condition is this one. Okay. Okay, then. Yeah, I don't have any other choice to write this like this. Then this is the condition, right? Then our condition is that mu has to be larger than 1 square root of a pi. Sorry? Yeah. Well, there is something. Okay, what is exactly that we are? No, because it's not as stronger, because here you have solutions that are not zero with a larger exponent. Okay? The larger the constant, the better for me. Okay, how? Let's see. let's see why I don't get. Well, let's see. Okay, this is what we prove. This. Okay. Okay, we claim that this is. Okay, this is. Certainly, we prove this theorem. How we compare this theorem with this theorem, that's the question. Right? We multiply by pi, our condition was. No, because we are. Wait. I think that, okay, give me another chance to do this. I multiply by pi and divided by pi. Multiply by pi and divided by pi. And then the condition is that let's see. I have mu here. I have mu. My problem is I don't know how to put, I have this condition with this pi there. How can we remove the pi and to compare with this one? Okay. I'm sorry? I did right? Okay, this is exactly the same if I write this like this, right? Okay. Then I divided by, no, I did wrong. Is this correct what I did that? Now I multiply by pi, divided by pi squared in both sides. And now I baptize that, the new mu. And this is A. This is the new mu, larger than 1 over pi squared. Okay, that means still I have the same thing. Okay, you cannot, then let's see, is this, you cannot be stronger than this theorem, otherwise we have something empty. I mean, this is sharp. You have, there exists solution with A equal to 1 that satisfy this and not 0. Okay? There exists solutions different than 0 such that you have this. I mean, we can construct this. You take belong to L2. Okay. Then with 1, you have that, you can prove that after 1, you start to be 0. Here, we have some error though, then, not? No, it's larger than that. Isn't it? Yes. From here on, you say that you are 0. Right? Then let me check my note to see where do I have. Okay, and then I have this. Let's see. Let's see what is exactly that we have wrong here. That. We should have a theorem that our theorem should, my theorem, when I prove it, was pi squared over 8. Then I have the pi in the wrong way. Okay? Where do I have the pi in the wrong way? My theorem should be this one. This should be my theorem. And it's very close to 1. Where did I miss the pi? Let's see. Where did I miss the pi? Okay, we have a, this should be the result. But we are off for the pi. Okay, where do we miss that? We have to go back and where do we miss the pi? Okay, it doesn't seem that the error is here. It seems that let's go back and see our condition of the Hardy one that we wrote. Okay, let's go back to see if we wrote this. If not, then we have to x squared, and it was u at time 1 e b pi x squared belongs to L2, and AB positive, and 8 times b times 4 pi t more than 1 implies 0. In fact, more or equal. Okay, let's try to see if we rephrase this in the right way. We put t equal to 1. This is a square here. That's the error. I put the condition here. Yeah. Yes. Then this is the condition that you get when you apply Hardy. And the condition here, if A is equal to B, then is that A is larger or equal to 1 over 2 pi. Okay? Okay. A times B I'm sorry? 4 pi. And what's the condition that we get there, here? Okay, let's review our condition. It was this. This was our condition. And now you rewrite, multiply by pi. Then it's 8 times mu times pi squared, larger than 1, imply that mu is larger than pi over square root of 8. Is this okay now? Okay. This is where I made the mistake. The condition was this one. I put this condition here and this condition here. And you cannot put it in both. Then let's see what. Then let's see if we still have a theorem. Who is larger, this one or this one? And this is pi squared. Who is larger, this one? Pi squared is certainly larger than this. Okay, then yeah, okay. There is a theorem here. This constant is smaller, this constant is larger. This number is larger than this number. Then I need a larger power to guarantee. Okay, this is like this. I multiply by pi. I put pi here. I have this, then this. Yes, okay. This is the theorem that we prove. Okay. This is the theorem that we prove, and this is the Hardy theorem. Are we? Okay. Say again. Here? Okay. Let's say I multiply by pi here, by pi here. This is okay. I put mu pi, and this is the condition. Okay. I multiply by pi both sides. Okay? And then the condition is a mu squared. And this is, I put mu here. Is this okay? And now this implies that mu is larger than 1 over the square root of 8 pi. Okay. And still don't have it. Okay, yes, this constant is greater than this constant. Yeah? Okay, thank you. I'm sorry that I got completely mixed up with the arithmetic, but it happened to me all the time. Then I'm not trying to excuse. Okay, the theorem says the following. If we have the same decay and type 0 and type 1 that we have to remove this, but it's simple to compare. If the constant is larger or equal to that, you have 0. We prove with this. Of course, we didn't prove because all the proof is here. Right? Under this assumption, then we have to insert the pi. We insert the pi, we have this, and we are not too far. I mean, the Sharp theorem is 1/4, and we are into 1 square root of this. It's a factor of square root of 2. Okay? Okay. Then, after some technical difficulties, we prove something, right? Formal. Now we have to prove this claim. You see that the proof of everything here, it was formal. You say, this is the equation that I have. I multiply by the weight that I want to consider, this in L2, right? Then I look for which function f, that is the u with the weight, which equation satisfy. For this one, right? For this one, I'm going to prove that if have the nice property that is almost logarithmically convex, is bounded below. When you are bounded below this way, you have logarithmically convex with this, and then all the techniques reduce to what we did before. Then everything is going to reduce now on to prove this inequality. Is this okay? I mean, I apologize for the 10-minute constant problem because... Okay, now how do you prove that? Okay, let's try to prove this proof of the claim. Okay, we are going to do this proof several times because we want to extend things to this setting when we are out of the Fourier transform, but let's not do it, go ahead of time. Okay, then this is our equation. Let me write the equation there. Okay, then we have this equation. Laplacian minus you can write this in two pieces. You can write this in this way. dt of u is equal to s of f plus a of f, where s is equal to this operator plus multiplication by this, and a is equal to the other side. Okay, why do you want to do that? Because S is symmetric. And A is skew-symmetric. Okay, the Laplacian is symmetric, but you're putting an I there. Multiplication by a real function is symmetric, but you're putting an I there. This operator, let's see if I put this. Together, this all together is symmetric. Okay? When you integrate, let's see that. If you have S of B multiplied by B, it's going to be integral of minus A 2 gradient of phi, gradient of b, multiplied by b conjugate, minus I, Laplacian of phi, multiplied by b, like this, right? Then you want to integrate by part and change this here. Then you integrate by part. You have this is I, and then you have 2. This go here, and this is going to be 2 phi Laplacian of b conjugate minus or plus I 2 when this hit here. Okay. Okay, then I need to pass everything to the other side. Then this has to appear here, this here. Then what do? We integrate this by part here. One pass here, and the other one pass to the other side. No. What they have done here? I'm sorry. No, I'm sorry. I need to pass these derivatives to the other side. I pass this derivative here. I have 2 Laplacian of phi, b, plus I pass this derivative here. This derivative here. I 2 gradient of phi, b gradient of b. And then you have it, because this one cancel one of these, then you're going to have this is I, b, Laplacian of phi, like this. I write it this. And you can write it like this because this is real. And this is going to be plus I, and I can write this way, 2b gradient of phi. Then you have exactly this. Okay, because you have the I there is a 2 here. Then you have this is exactly b s of b. Okay, this is symmetric. And this is skew-symmetric. Okay. Is this okay? Okay. Uh-huh. This is F. Thank you. F. Thank you. This is F. Thank you, Herman. Is this okay? This one here? Square here. Okay. Okay. Okay, answer. Okay, now we have this. Well, suppose that you have H of T is the L2 square norm of F. Okay. Then I'm going to prove this now in the abstract version of this. Then who is h prime of t? Is dt of f plus f dt of f. This is equal to this. Who is dt of f? Is s and a, and I put s and f plus f, s, and f. Why this is true? Because, okay, let me do it into a step. St is equal to this, sf plus af of f plus f sf plus af. But since you are skew-symmetric, you have this. Right? Then you have 2 times the real part of sf by f. You can forget this part. This with this cancel, this with this cancel. Then you have this one plus this one. And this is twice the real part of this. Okay, and using that A is skew-symmetric. Okay. Then who is the derivative of the log of h? Then is h prime over h, that is exactly equal what you have here, 2 times the real part of sf f divided by h. Then who is the second derivative of the log? It's going to be the derivatives of this. Let's compute the derivatives of this with respect to t. Now we have to compute this one, right? Then the derivative with respect to t of I have to take the derivatives of this. The derivatives of twice the real part of sf f. This is equal to twice the real part of what? When the derivative hit here, you have dt of f. Plus, when the derivative hit the first one, plus when the derivative hit the second one. Okay. Let me write this like this. I don't want to put the real part here. I will do it like this. Derivative with respect to t of all this is this. We know that we have to real part. Let's do it by pieces. It's that one. Derivative hit here, derivative hit here, derivative here. Who is this? Then this is exactly equal to dt of f plus twice the real part this is symmetric. I can pass this operator here. This is the real part of this. Do we believe that you can pass this by symmetry here. Then you have this number, and his conjugate is twice the real part. Is this okay? Then this is exactly equal to ST of FF plus this dt of F this is S of F plus A of F, S of F. Are you with me up to here? I use that this is an identity. Okay. Now this is equal to ST of F, F plus. When you use S with S, you have twice SF, SF, and now I have SA, F, SF, but this is the real part. I have to put this and his conjugate, that is this one. When I multiply this with this is real. I have got this. When I multiply this with this and I have the real part, I put this and his conjugate. Okay, now this part is equal. If I pass S to this side, I get this because it's symmetric. If I pass A to this side, I have this. Therefore, all this come to be equal to this. ST of F, S, F, F, plus the commutator of S and A applied to F, F, plus S of F, S of F. Okay. Therefore, we have that. Let's write this here. ST of SF by F is equal to ST S F F plus S of F S of F plus the commutator S A of F F. Okay. Can I erase that? And let's call this quantity N of T is SFF. This is D. But if I want to be D. Okay. 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 Therefore, this is exactly equal to 2. This is real because you don't have to put the real part because S is symmetric. Then this is S dt ht. Then the derivatives of the log of h is that. The derivatives of this is exactly twice derivatives of t h of t prime. Right? And this is what is called the frequency function when you are working with Klainerman. But doesn't matter. What is this? The derivatives of this is twice d prime t over h minus d h prime h squared. And we have everything that we need because this is the derivative. This is derivatives of dt. Okay. Now we know what is the derivative. We can write it like this or like this, whenever you prefer. Yes. Okay. We know who is h prime. H prime is this. That doesn't have to put real. D prime is what we have there. Okay, let's write everything. Okay. D prime is all this. Then it's going to be equal to ST plus S commute with A applied to F multiplied by F then I took this term and I took this term. Okay, I missed something here. I missed a 2 here. Let me do it again. Let me do it again, and I'm sorry. Answer? There should be a 2 here in front. There is a 2 there? Okay, there is a 2 there because there was a real part, and okay, there is a 2 there. Otherwise, okay. Then I have this. Then I have plus. There is a 2 here that I missed when I wrote from here to there. Now I have this part, 2 SF over FF. And now we have minus, who is H, the derivatives of H. The derivatives of H is this one, is 2 dt, right? This is what we defined. Then this one, we have d of t multiplied by the derivatives of h, that is 2, divided by h squared. I claim that this is positive. Okay, let's write who is this. This is 2 SF, F times F, multiplied by F, divided by FF. Okay, this canceled if you wish. Minus 2, who is this? SFF, divided by F. Then it's clear that by Cauchy-Schwarz, this is larger than this. Okay, this is the what you have in the top. The bottom and the bottom are the same by Cauchy-Schwarz. You have. Then the only thing that remains to prove, then we have reduced the matter. We have reduced the matter of proving that the log of h double derivatives of this is larger than okay, now which is the number that we have here? 3, 2, 1. Proving this, to prove what? That this quantity with a 2 in the front is larger than this. Okay, because we remove a piece that is positive. Then the second derivative of the log of the h is this piece plus something that is positive. Then we have to reduce to this. Then in the next class, say again? There is a 2 here, right? A 2 here, thank you. In the next class, we are going to do the commutator between this and this, and prove that the commutator of these two is almost positively defined. Right? Then you have two pieces, the commutator that always gives you something better, and the derivatives of the operator S with respect to t, component-wise. Then we're going to have this piece. St is this. And then we have to compute the commutator and see that this is almost positively defined. In fact, it's bounded below by this number. Okay, we'll stop here, and we didn't cover all that we wanted because we mixed up the constant, but that's a